Hello friends, welcome back to another Calculus 2 video. In this video, we're going to do something quite remarkable, probably the most remarkable thing we've done up until this point, and probably will do all class. And that is to totally expand our geometric conception of volume. After this video, we'll be able to find the volumes of infinitely many shapes. But first, let's start with familiar territory. Let's start with the rectangle. And suppose I were to ask you, what is the area of this rectangle? Of course, you'd say, 2 times 4 is 8, standard geometry problem. But what does that mean visually? Conceptually, that means the number of unit squares that I can jam into my two-dimensional region, in this case a rectangle, without overlapping, of course, is 8. 2 times 4 is 8, the number of unit squares. Likewise, if I were to ask you what is the volume of this rectangular three-dimensional solid, you'd say, of course, length times width and height, 24. But what that means is that I have 2 times 4 number of unit cubes in my bottom layer, and I have 3 layers, which is my height. So all in all, I have 24 unit cubes, jammable without overlap, into my rectangular solid. That's what volume is, and length times width gives us the number of unit cubes in the bottom layer, because the number of unit cubes in the bottom layer is the same as the number of unit squares touching the ground, so to speak. So imagine the bottom of that solid. If you're looking at it from the bottom, you'd see 8 unit squares touching the ground, 8 unit cubes in my bottom layer, and it's exact same idea here. Let's say we have a nice right circular cone. I were to ask you, what is the volume of this right circular cone? Cylinder, my bad, y'all. Number of cubes in the bottom layer, just as length times width provided the answer to this for the rectangular solid, pi r squared is going to provide the answer in this case. I have pi r squared unit squares touching the ground, and that's the number of unit squares in my bottom layer. Multiply that by the height, and voila! In one fell swoop, we have proven, just through pure conceptual analysis, the volume equation for a cylinder. Really, the groundwork for it was laid by the area of a circle formula we proved in class. And this works for any cylinder. Doesn't matter how thin it is, doesn't matter how flat it is, like the flat one I've sketched out down here. If it is a cylinder, the volume is given by pi r squared times height. Pi r squared times height. And now you may be wondering, why did I bother drawing a flat cylinder? Well, this flat cylinder has a special name. It's often called a disk. And he's going to prove very useful. In fact, he's going to be the key piece in us finding the volumes of infinitely many shapes. Let's see how that works. So we'll start in familiar territory. I give you a piece of a graph, a function on an interval a to b. And standard thing, I shade that region there. It's a nice calculus 2-ish thing to do. Shading on in. But now, instead of asking you what is the area bound between the x-axis and the graph, I'm going to rotate that entire two-dimensional region around the x-axis to generate a nice solid like so. It looks kind of like a vase or something you'd put a candle on if you were to tilt it upright. And let's give him some solidity in his interior. Let's give him a little panache on the top. That's where you put your candle. But yeah, this is a three-dimensional solid. And now let's clean him up just a bit around the edges. There we go. Now he's a fully fleshed solid. We're going to call this solid a solid of revolution. And now we're going to ask quite a daring question. Given that I know the function that I used to create this solid and the x interval over which I rotated, what is the volume of that solid? What is the volume of it? Is it possible to find the volume of that solid given that we know f and we know the x interval a to b? Is there any way to find the volume of the solid? Well, in fact, ladies and gents, there is. What we're going to do, we're going to start in familiar territory. We're going to start with the usual rectangular approximation for area, but we're not going to find the area. We're going to draw these right endpoint rectangles. I chose them to be right endpoint rectangles for convenience. But now, after drawing them, instead of finding those rectangular areas and adding them up, I'm not going to find any area. I'm going to take each of those rectangles and rotate them around the x-axis. That will create n cylinders. So n right endpoint rectangles, rotate each one to create n cylinders in total. These n flat cylinders that we call disks. But whether the cylinders are flat or thin, we find the volume in the same way. So let's see here. And of course, the sum of those n cylinders will serve as an approximation for that vase, that candle holder lying down on its side up on the right. It will be an approximation. It'll be an approximation, and you may see already where we're going with this, familiar calculus thing, but for now let's just draw the solid approximation. So here I'm drawing cylinders, you're seeing them from the side. I'm going to shade them so you can get a sense of their three-dimensionality, their meatiness, their thickness. So there we go. Here is my approximation of the vase with flat cylinders that you are looking at perfectly from the side. And now, suppose also the width, of course, is the same for each one, delta x. And let's compute the volume of just any one of these. Over here on the left, you're seeing me. We're drawing just the x-coordinates, x1, x2, x3, x4, right endpoint rectangles. Now I'm taking one cylinder, laying it flat. That's what I just did here on the right. Now, given that flat cylinder in its more normal orientation, lying flat on the ground, so to speak, what's an expression for the volume of it? Well, of course, it's going to be pi r squared times height, but what is h in this particular case? What is height in this particular case? And what's the radius? Well, the height is delta x. The radius, which I'll draw here in pink as well, and now I'll take that and draw that in pink as well on the leftmost graph. That is the function value of, in this case, the fifth one, f of x sub 5. And what's f of x sub 5? Well, x sub 5 is a plus 5 delta x. We're using right endpoint rectangles. So that's the radius in this particular case. So the volume of this, in this case, the fifth cylinder I picked out, is going to be pi times 5 f of a plus 5 delta x squared all times delta x. And of course, I could have done that with the same process with the first cylinder, the second cylinder, the nth cylinder, and adding all those up gives me an approximation of the solid of revolution. So here he is. Here he is up here in the top left. The cylindrical approximation using n cylinders has a sum of those n cylinders. So pi f of x1 squared delta x, pi f of x2 squared delta x, all in all the way up until the nth one. Now we're just going to replace x1, x2, xn. We're using right endpoint rectangles with a plus delta x, a plus 2 delta x, a plus n delta x. And this allows us to crisply compress this info into a summation symbol. And here we are. That is our standard way of compressing right endpoint rectangle summations. Of course, the pi I can yank out of the summation, leaving me with pi all times the sum of that guy right there. And he looks awfully familiar, but there's that squared. I'm squaring some function. I'll deal with him in a second, but now, of course, to get the exact volume, solid revolution, we let those n cylinders get infinitely thin. Infinitely thinize those n cylinders, and that gives us the volume of the solid of revolution upon addition of them. And now expressing that just a little more mathematically, limit as n goes to infinity of all of that, pi summation f of a plus I delta x squared delta x. Of course, I can yank out a pi from a limit. I yank the pi out of the sum. I can yank it out of the limit as well. And now let's analyze this limit term just for a second. I know that my function f is continuous on a to b. It has to be, otherwise I'm not generating a solid, right? So I'm going to call a new function g, f of x, the entire thing squared. And as you know from Cal 1, if you multiply a continuous function by a continuous function, in this case f times f, the result is also a continuous function at that point on that interval, and so forth. So g must be continuous as well, so we can rewrite this sum, which I will write. Had to erase my nice approximation picture. Okay. But I'm just going to replace the f squared with a g. And the point of doing this is so you can clearly see what this limit is equivalent to saying. This limit here, excluding the pi, forget about the pi for a second, but this limit here perfectly matches the form of the definite integral of g from a to b, lower bound a, upper bound b. We are bringing integration into the picture. This, again, the same thing. Symbolically is this right here. And there we have it. We substitute that in. Now we substitute back in f squared for g. And we get exactly what we need to find the volume of that solid of our evolution. I just need to know that particular function that I drew at the very beginning, square it, integrate on my x interval of interest, and that gives me the volume of that vase, that candle holder. So using formulas like this, we can find the volume now of infinitely many three-dimensional shapes. And let's illustrate those. Let's try to find the volume of a weird shape that we had probably never considered before. So here's an example. Let us, how about we have two parabolas. I'll let one be a downward facing parabola. How about 9 minus x squared, so positive y-intercept of 9, but facing downward. And its counterpart, an upward facing parabola with a negative y-intercept of, well, actually, I don't need to do that. I'm not finding the area between graphs. I just need one parabola. And I'm going to revolve the region bound by that parabola and the x-axis over the x-axis. So there we are. I'm going to take that the green region, and I'm noting its x-intercepts in red. So I find the POIs to give me my x-interval of interest. -3 to +3. Revolve him right around that x-axis, ladies and gents, so we get this chestnut, walnut, peach thing. But yeah, we're going to find the volume of that thing. And how do we do that? Well, all we have to do is apply the formula down there. -3 to +3, stick it with a pi out front, square the function. Don't forget to square that function. It's a radius. And upon doing so, we get this nice mathematics here. Computing our numbers, let's see. It's gonna be like so. Just gotta be careful at this point. Gotta be very careful with making sure you're sticking negative signs where they need to be, not forgetting negative signs. But yeah, just like you guys did for finding the area between curves, just keep track of that stuff and you'll be good. Just a little further, and I can factor out -1 to get plus the same thing. That's what I did in that second bracketed term right around the middle level of the chestnut. So that's where the 2 came from, and now it's an arithmetic problem. It's a nice arithmetic problem. 2 times 81 plus 243 over 8. Over 5 it looks like. And yeah, doing that gives me this. That is the volume. We just found the volume of this bizarre, creepy looking shape. The volume of this chestnut football is 1296 pi over 5. That's the number of unit cubes we can jam into that figure without overlap. So again, I can't emphasize enough. Using these ideas, this idea in particular, we can find the volume of infinitely many shapes. Infinitely many weird shapes. So just like in Cal 1, well, before that, so let me just illustrate why. Again, this is the radius. So in purple there, you see a little cylinder, a little radius I've drawn, a little thin slice, rotated around the x-axis. So indeed, the function is the radius of the cylinder, and dx is the infinitely thin height, if you were to reorient this vertically. So yeah, let's do 2 more things. Let's harken back to 9th grade geometry and prove some familiar stuff. So let's step away from the weird shapes and prove some familiar shapes, like volume of a sphere or the volume of a cone. So yeah, we can do a lot with this formula. So again, just like in Cal 1, we were able to find the slopes of weird shapes. That represented infinite expansion. And like at the beginning of Cal 2, now we found the area of infinitely many two-dimensional shapes. We can do the same thing with volume here. And now we can even prove familiar formulas from 9th grade geometry. So first is a sphere. How do we generate a sphere? Well, a nice way is just to take just a generic semicircle and swivel it right on about that x-axis. That little region form that semicircle, swivel that around the x-axis. Keep it generic, so an r and an r. There's the function, the square root of r squared minus x squared. Just shading him in blue, I'm going to rotate him around the x-axis to generate a sphere. So right rotation, and voila, there's my nice blue moon sphere. That looks quite nice. Or maybe it's just because I haven't had breakfast yet. This creates a sphere. It creates a sphere clearly. And the volume of this solid, yeah, look how crisply it's going to come out. I'm going to square that function and get rid of the square root. So this is a very simple integral. R is a constant, x is my variable of integration. So pi all times r squared x minus x cubed over 3. I evaluate it from negative r to positive r, and I do that. And let's see what happens. Will it come out to be 4/3 pi r cubed, or will it not? We'll just have to wait and see. But it should. Hopefully it will. And I get some common denominators, and I get 4/3 pi r cubed for my volume of a sphere. By the way, notice how much simpler this proof was than proving the area of a circle. Yeah, you may think, oh, well, why is that the case? Well, no, remember, we are presuming the area of a circle formula in everything we are doing right now. The area of the circle formula was the foundation for the circular cylinder formula, and the circular cylinder formula is the foundation for what we're doing right now. So we couldn't be doing any of this without the area of a circle formula. And by extension, we proved that area of a circle using rectangles. So it all falls back to the simple, innocuous rectangle. Since we're doing all this with rectangular areas. Now then, same thing for a cone. I'm just going to take a generic line segment, completely arbitrary, meaning completely arbitrary length, arbitrary slope, and I'm shooting it off from the origin into the first quadrant without loss of generality. So arbitrary length, arbitrary slope, and you may notice with that arbitrariness, if I swivel the resulting 2D region around the x-axis, I will create, for some reason, a blue cylinder. He became blue. That's fine. We like blue. Green can become blue, but not vice versa. I had a toothbrush once that was blue and it turned green. That was not good. But green to blue, that's okay. So we have created an arbitrary cylinder. The radius, generic r, the height, h. If we're tilted on its side. So let's transplant r and h back onto our picture. What are they on this right triangle here? Well, clearly that's going to be the h, the horizontal part, and that's going to be the r. And in one fell swoop, I can find a function for that line. It goes through the origin. That line segment, has to have a y-intercept. So the y-intercept is 0. M, the rise of a run, is r over h. And I got a nice equation for my upper bound of my region, my function. It's the same thing. I integrate from 0 to h, because h is on the x-axis in this case. And there we have it. It's a really simple integral. You would think this formula would be so tough to prove, but just like the sphere formula, the cone formula as well, it just comes out to be a nice 1/3 pi r squared h. Once more, the groundwork for this was the right circular cylinder formula. That's the whole basis of this volume of revolution formula, the circular cylinder formula. And the basis of that is the circle formula. The area of a circle formula, and the basis of the area of a circle formula is the rectangle, is the mirror rectangle. So, we have laid the groundwork already for, finding these volumes very swiftly. Now, let's try a more difficult problem. What if my two-dimensional region that I'm swiveling around the x-axis, or whatever, it doesn't have to be the x-axis, and we'll talk about that later. What if the lower boundary of that region is not concurrent with, is not collinear with the x-axis. So notice in every volume thing that I've done so far, with the first chestnut football thing, and the semicircle and the line with the triangle, the lower boundary of the region was touching the x-axis everywhere. It was concurrent with, it was collinear with. But how about I swivel this region, the region bound by these two graphs, around the x-axis? Alright, well first I want to handle on what this region looks like. So, same kind of deal I did in the last video. I find the POIs, and I'm going to sketch a picture if I possibly can. I set them equal. One's a parabola and one's a line. And let's get some POIs. Let's get some POIs. Now then. Just doing some math arithmetic here, and I can factor that right side, I hope, and my hope is rewarded. There he is, and x ends up being 1/2 and positive 6. So again, we know this is a line and a quadratic, a classic story. A much better love story than Twilight. And here in my coordinate plane, I can now sketch a pretty decent picture of what's going on. I'll designate the parabola in blue and the line in red. Quadratics. Quadratics, so it's always good to graph the vertex. Where's that vertex? Negative b over 2a for an x-coordinate. That's a positive 3. And I know this is a downward-facing parabola, because again, I simplified that into a negative x squared plus 6 in my math on the in white. So there's my parabola, my parabola. I like parabola. I like that word better than parabola. Parabola makes it sound like you're getting somewhere. It's like the start of a good journey. So there's my line. Y-intercept of 3, slope of negative 1/2, and the intersection POI of 6. So there is the region. I'm swiveling around the x-axis, and again, notice that lower boundary of the two-dimensional region in red is not, unlike the last 3 problems, it's not touching the x-axis everywhere along the interval of interest. Most of it, or all of it except at one point, is above. So when we swivel this around the x-axis, we're going to create a hollow space, as it were. Notice we didn't create a hollow space anywhere in the solid for the chestnut / football. For the sphere, of course, no hollowness there, no hollowness in the cone. But no, we swivel this around the x-axis, we're going to create a nice little hollow interior. Nice little space within, so to speak, our 3-dimensional region. So how can we take this complication into account? Well, we just engage in a simple part-hole analysis that we started in beginning of high school. I'm going to represent that region that I'm trying to find, that 3D region I'm trying to find, with 3D regions I know how to express immediately in integral form. If I swivel this blue 2D region around the x-axis to create a 3D solid, and I swivel this 2D region down here in red around the x-axis to create another 3D solid, if I subtract the resulting blue solid, let's say, if I take away from it the resulting red solid, then the solid of revolution formed by revolving R1 minus the solid of revolution formed by revolving R2 is going to equal the volume of the thing I'm trying to find. So here I'm just noting a few things. I want to do this because R1 and R2 I can immediately again set up integral expressions for. R1 and R2, their lower boundaries are completely on the x-axis on the interval of interest. And we like that because again, we can immediately set up an integral expression using the formula we've been using for the last 3 examples. So what are they? So let's see, that first one, R1, the radii of each cylinder is going to be the function value of the parabola. So I square that function value, 9 minus x minus 3 squared, the entire thing squared. Likewise, if I revolve that 2D region in red, well, the radii of that are going to be the function values of the line. So I square those values, put them in the integral. Now I'm integrating from 1/2 to 6. And again, if I subtract by saying v solid r1 minus v solid r2, I get what I'm trying to find. What is that up there? And I'm just going to express this here in some color. So the blue is going to equal the red plus the green. Again, it's simple part-whole analysis that you all started in 9th grade geometry, but just now with some fancier calculus notation. That's all that's going on here. So, let's go ahead and solve for what we're trying to find. It's high time we do that. Subtract both sides by the red volume of the V, volume of the solid formed by revolving R2, and we get an integral expression minus another one. That guy minus that guy. And now, the bounds of integration are exactly the same. I got a pi in front of each one, so I can smush these all into one integral like so. And this problem just wanted me to set up an integral expression, didn't want me to actually find the volume. So, and many problems in your book on AP exams, exams in general, will just ask you to set it up. They have faith that you're able to, do the computations. So just set it up so you know conceptually how to do it. But notice if I call that top function f, that lower function g, I can express this more tersely, formula-wise, as volume of the solid is going to be equal to pi times the integral from a to b, lower bound to upper bound of the top function squared minus the bottom function squared. And we'll talk about this more in class and in future videos as well. That top function is sometimes called the big radius, capital R, and the other one's called the small radius, lowercase r. So if we have this formula here, we can account for hollow spaces, but a key thing, it's not the only formula we can use. There's another formula in a method called the shell method that'll also give us the ability to find volumes of solids of revolution that have hollow spaces within them. Thanks for listening.